We'll start in a minute. Today we'll be looking at some problems in Chapter 8, Section 3 again. This is Part 2 of the Rational Exponents. Two definitions that we saw last time. If n is a positive integer, then the nth root of a can be written as a to the exponent 1 over n. So on the left, we say that that's the radical form, and on the right, that's the rational exponent form. But if we let m and n be positive integers, we can also write this definition. The nth root of a to the m is a to the m raised to the exponent 1 over n. Then applying a property of exponents, multiply the exponents, we can write it as a to the m over n. And that's the same as a to the 1 over n raised to the power m, or the nth root of a raised to the power m. So we use these definitions to our advantage. Let's start by simplifying some expressions with rational exponents. This first one, 27 raised to the 4/3 power. The denominator of the exponent is 3. So we can think of this as 27 to the 1/3 raised to the 4th power. We're just applying a property of exponents. And 27 to the 1/3, 27 is a perfect cube. So 27 to the 1/3 is 3. And then 3 to the 4th is 81, because 3 times 3 times 3 times 3 is 81. Okay, the next one, 216 to the 2/3. The exponent is 2/3. The denominator of the exponent is 3. And 216 is a perfect third power, or a perfect cube. So we can rewrite this as 216 to the 1/3 raised to the 2nd. And then the cube root of 216 is 6. So this is 6 to the 2nd. And 6 to the 2nd is 36. So remember, in this course, things work out pretty nicely. In both of the first two cases, the denominator of the exponent is 3, and the base number is a perfect cube in both of those cases. Okay, the next one, part C, negative 25 to the 3/2. So whenever negatives are involved, you have to make sure that you do the right thing. Negative 25 isn't in parentheses, so the exponent 3/2 applies to 25. You can think of negative 25 to the 3/2 as negative 1 times 25 to the 3/2. And then we'll simplify 25 to the 3/2 and then afterwards multiply it by negative 1. So negative 1 times, and then 25 to the 3/2. Think of that as 25 to the 1/2 to the third. 25 to the 1/2 is just the square root of 25, which is 5. So this becomes negative 1 times 5 to the third. And then 5 to the third is 125. And then negative 1 times 125 is negative 125. That is our final result on that one. Okay, the next one, now we have a variable involved. Inside the parentheses, we have 64x to the 5/7. And this entire term is raised to the 1/6. So the first thing we can do is we can apply the property of exponents where we multiply the exponent 1/6 times each of the exponents on the factors on the inside. Think of 64 as 64 to the first. So we multiply the exponents 1/6 times 1. We have 64 to the 1/6 times x to the 5/7 times 1/6. 64 is a perfect sixth power. 64 is 2 to the 6th. So we'll write that as 2 to the 6th to the 1/6. For the other term, we can go ahead and multiply the exponents. 5/7 times 1/6 is 5/42. And then 2 to the 6th raised to the 1/6, we multiply the exponents again. 1/6 times 6 is 1. So we get 2 to the first, but 2 to the first is just 2. And our simplified answer is 2 times x to the 5/42. Okay, the next one we have inside parentheses, we have 3 factors, 4 times x to the 2/5 times y to the 3/5. And that entire product is raised to the 5/2. So we distribute multiplication of the exponent 5/2. We multiply 5/2 times each of the exponents on the 3 factors on the inside. So remember, 4 is 4 to the first. So when we distribute this exponent, we write 4 to the 5/2 times x to the 2/5 times 5/2 times y to the 3/5 times 5/2. 4 to the 5/2. The denominator of the exponent is 2. And we know that 4 is a perfect second power, or a perfect square. So we'll rewrite 4 to the 5/2 as 4 to the 1/2 raised to the 5th power. For the next term, x to the 2/5 times 5/2. we get 10 over 10 for the exponent, which is 1. So x to the first. And then for the third factor, we multiply the exponents. 3/5 times 5/2 is 3/2. So we get y to the 3/2. Okay, 4 to the 1/2, that's the square root of 4. That's 2. So we have 2 to the 5th times x. When the exponent is 1, you don't need to write the exponent. So 2 to the 5th times x times y to the 3/2. And then 2 to the 5th is 32. So our final answer is 32 times x times y to the 3/2. And the next one, we have y to the 5/3 times y to the negative 1/3 divided by y to the negative 2/3. Well, there's only one variable involved, and we're multiplying and dividing. So the final result that we want the variable y to appear only once and with a positive exponent. So we can go about it in a couple of different ways, different yet equivalent. So let's just simplify the numerator. Since the bases are the same, the base is y, we can simplify the numerator by adding the exponents. So we have y to the 5/3 plus negative 1/3. And we'll leave the denominator the way it is for the moment, y to the negative 2/3. And then in the numerator, we add the exponents. 5/3 plus negative 1/3 is just positive 4/3. So the numerator becomes y to the 4/3. And the denominator is y to the negative 2/3. Since we have a y to the negative 2/3 in the denominator, well, you can go about it a couple of different ways. Remember that y to the negative 2/3 in the denominator is equivalent to y to the positive 2/3 in the numerator. And there's a factor of 1 that stays behind in the denominator, as usual. And then y to the 4/3 times y to the 2/3 divided by 1 is just y to the 4/3 plus 2/3. 4/3 plus 2/3 is 6/3. And 6/3 equals 2, so our final result is y to the 2nd. Okay, let's move on to the next page. Number 2, convert the expressions to radicals and simplify if possible. So the first one, x to the 3/2. The denominator of the exponent is 2. So when we convert it to radical form, the index is 2. And then we have x to the 3rd as the radicand. So here we're just applying this definition. If you have a to the m over n, then that's the nth root of a to the m. Okay, we can simplify this. We've simplified square roots before. The largest factor of x to the third that is a perfect square is x to the second. So we can rewrite this as the square root of x to the second times x, because x to the second times x is x to the third. And the square root of x to the second is x, which we multiply by the square root of x. So you can put the index 2 in there if you want, but when the index is 2, it's not required because it's a square root. Okay, the next one, we have 5x in parentheses to the 2/3. Convert that to a radical. Well, if we're going to convert it to a radical, the denominator of the exponent determines what the index of the radical is. So the index is 3. And then inside the parentheses, so here again, make sure you're careful. So we put 5x in parentheses and square the entire term 5x. So this is a correct answer, but you can also square the term 5x and write it as the cubed root of 25x squared. So if you don't include the parentheses, and if you write 5x to the second without parentheses, then that's not correct. So I'll make a note up here. But remember, this is not equal. The cubed root of the term 5x to the second does not mean the same thing as the cubed root of 5x to the second. Those are not the same. Here, the next one, x to the 7/4. The exponent is 7/4. Convert it to a radical. The index of the radical is 4, and the radicand is x to the 7th. Okay, that's a good start, but we can simplify further. The largest factor of x to the 7th that is a perfect fourth power is x to the 4th. So we can rewrite this as the fourth root of x to the 4th times x to the 3rd. Which is the fourth root of x to the 4th times the fourth root of x to the 3rd. And then the fourth root of x to the 4th is x to the 1st, or just x. And so the final answer is x times the fourth root of x to the 3rd. This is our simplified result. Okay, the next one, 8x to the 5/3. Convert this to a radical. So the index of the radical is 3 because the denominator of the exponent is 3. And inside the parentheses, we have the term 8x to the 5th. Well, this can definitely be simplified. So let's consider, with a calculator, it's not too hard to do. But without a calculator, let's first, before converting it to a radical, let's write this. The term 8 times x to the 5/3 is 8 to the 5/3 times x to the 5/3. And 8 to the 5/3 is 8 to the 1/3 to the 5th. 8 to the 1/3 is 2. And then we have 2 to the 5th times x to the 5/3. And 2 to the 5th is 32. And so we have 32 times x to the 5/3. If we do it this way, note now that 32 has been, this is the simplified answer of 8 to the 5/3. And so this exponent 5/3 applies to x only. So we can write 32 outside of the radical. So 32 times the cubed root of x to the 5th. But the cubed root of x to the 5th can be simplified because the largest factor of x to the 5th that's a perfect cube is x to the 3rd. So there's a couple of more steps left. We can rewrite this as 32 times the cubed root of x to the 3rd times the cubed root of x to the 2nd. And the cubed root of x to the 3rd is just x. So our final answer is 32 times x times the cubed root of x squared. So this one was a little more involved, but it's a good exercise for you to work on. Okay, the next one is pretty easy by comparison. Convert y to the 2/5 to a radical. So the index of the radical is 5, and the radicand is y to the 2nd. And this cannot be simplified any further than it already is. Okay, the next one let's apply the outer exponent first. So we have 7 to the 3/4 times x to the 8 times 3/4. Uh, 8 times 3/4 is going to simplify to an integer. So let's rewrite 7 to the 3/4 in radical form. So the denominator of the exponent is 4. And so inside the radical, we have 7 to the third. And then x to the 8 times 3/4 is just x to the 6th, because 8 times 3/4 is 24 divided by 4. So there's only one number that's inside the radical. X to the 6th is entirely outside of the radical. And we can simplify a little bit further, because 7 to the third is just 343. So this is the 4th root of 343 times x to the 6th. Okay, the next section of problems, we do the reverse operation. We convert the radical expressions to rational exponent form. Okay, the first one, the 7th root of x to the 5th. So this means x to the 5th to the 1/7. And then we multiply the exponents, and we get x to the 5/7. Okay, the next one, convert this to rational exponent form. So 3 is outside of the radical. And we have 2x inside the radical, so the term 2x to the 1/4. So this is an okay answer, but you can write it as 3 times 2 to the 1/4 times x to the 1/4. So 3 is just a factor. The exponent 1/4 does not apply to the factor 3 at all. Okay, the next one, the 5th root of 13x to the 4th. So inside the radical is 13 times x to the 4th. And the exponent is 1/5. Then we can write this as 13 to the 1/5 times x to the 4/5. So that's as far as we take that one. Okay, part D, 2 times the cubed root of 5x to the 2nd. So 2 times the quantity 5x to the 2nd to the 1/3 power. And we can write this as 2 times 5 to the 1/3 times x to the 2/3. Okay, part E, 5 times the 11th root of y to the 9th. So 5 times y to the 9th to the 1/11. Then multiply the exponents, we get 5 times y to the 9/11. Okay, part F, the 6th root of 10y. So the entire term 10y is raised to the 1/6 power. And we can write this as 10 to the 1/6 times y to the 1/6. That's as far as we can go on that one. So I'll just point out that we couldn't simplify any further than we did on those 6 expressions that we converted to rational exponent form. Okay, the next page okay, number 4, part A, 64 to the 5/2. So I'll give you a few seconds. I haven't asked you to answer any questions yet, so you can answer that one. Well, with a high-powered calculator, it doesn't take too long. But I didn't use a calculator. So you can think of this 64 to the 5/2 as 64 to the 1/2 to the 5th, because 5 times 1/2 is 5/2. 64 to the 1/2 is the square root of 64. So this is 8 to the 5th. And then 8 to the 5th is 8 times 8 times 8 times 8 times 8. And that's equal to 32,768. So with your TI-30, you can find that answer pretty fast. But you need to know how to go about it. Hey, the next one. So somebody else give an answer. Simplify the number negative 64 to the 2/3 power. Okay, the strategy here. If you have a number raised to an exponent that is a fraction, check to see if the number inside the parentheses is a perfect power determined by the denominator of the exponent. The denominator of the exponent here is 3. So remember, in this class, things work out really nicely. So is there a number that, which when raised to the third power, you get negative 64? Another way of asking that is negative 64 a perfect third power? Yes, it is. If you raise the number negative 4 to the third, you get negative 64. So an intermediate step is to write this as negative 64 to the 1/3, determined by the denominator 3, and then afterwards raise that number to the second power, which is the numerator of that exponent. So the cubed root of negative 64 is negative 4. And then we raise negative 4 to the second, which is positive 16. Okay, the next one, a similar type of approach. This one will be a little easier. 100 to the 3/2 power. The denominator of the exponent is 2, so we want to know if 100 is a perfect second power or a perfect square. So rewrite 100 to the 3/2 as 100 to the 1/2 to the third, because 3 times 1/2 is 3/2. 100 to the 1/2, or the square root of 100, is 10. And then 10 to the third, 10 times 10 times 10 is 1,000. Okay, the next one's simplify. Here we're just multiplying b to the 1/4 times b to the 5/8. The base is the same. They both are the variable b. So we write b to the 1/4 plus 5/8. We're just applying one of the properties of exponents that we learned a few weeks ago. And then 1/4 plus 5/8, we need a common denominator. So convert 1/4 to 2/8. So b to the 2/8 plus 5/8. And our final result is b to the 7/8. When the base is just a variable, we can't take it any further than that. The next one, 6 to the 5/2 times 6 to the 1/2. This time the base of each of those in the product is a number 6. But since it's the same number, we can write it as 6 to the 5/2 plus 1/2. And 5/2 plus 1/2 is 6/2. 6/2, or 6/2 is 3. And in this case, we can take it out further because 6 to the third can be expanded. 6 times 6 times 6 is 216. Okay, the next one, y to the 1/2 times y to the 3/4. We're multiplying and the base is the same. The base is y. So we add the exponents, y to the 1/2 plus 3/4. 1/2 plus 3/4 is 2/4 plus 3/4. And so our simplified answer is y to the 5/4. That is as far as we can simplify that. if we're going to leave it in rational exponent form. Okay, another property of exponents in the next row, k to the 12th raised to the 3/4. So this time we multiply the exponents and we get k to the 12 times 3/4. 12, think of 12 as 12 over 1 if it helps. 12 over 1 times 3 over 4 is 36 over 4. And 36 divided by 4 is 9. So this simplifies to k to the 9th. Okay, we do the same sort of thing on this one. A to the 15th raised to the 3/5. Multiply the exponents. So multiply 13 or 15 over 1 times 3 over 5. 45 over 5 is 9. So we get a to the 9th. Then x to the 10th raised to the 5/2. So what do we get for an exponent when we simplify x to the 10th raised to the 5/2? Yeah, x to the 25th. Because 10 times 5/2 is 50 over 2. 50 over 2 is 25. Okay, the next pair of problems, or 4 problems, number 5. Simplify 16 times m to the 1/3 all raised to the 3/4. So remember, 16 has an exponent of 1. We just don't normally write it. So when we expand this, we're going to multiply the exponent 3/4 times each of those exponents. And we start out by writing 16 to the 3/4 times m to the 1/3 times 3/4. And then 16 to the 3/4. Well, 16 is a perfect 4th power. The denominator is 4, so we're going to wonder if we can simplify 16 to the 1/4. So rewrite 16 to the 3/4 as 16 to the 1/4 to the 3rd. With the variable, we just simplify the exponent. 1/3 times 3/4 is 1/4. 16 to the 1/4 is 2, because 2 to the 4th is 16. So this becomes 2 to the 3rd times m to the 1/4. And then 2 to the 3rd is 8. So we write 8 times m to the 1/4. Okay, the next one. So I'll give you a few seconds to work on that. So if you haven't answered a question in a while, now's your turn. Simplify the quantity 9, x to the 2/5, y to the 3/5, all to the 5/2. Did you get an answer? All right, let's distribute multiplication by the exponent 5/2 to each of the other exponents. So 9 to the first to the 5/2 is 9 to the 5/2 times x to the 2/5 times 5/2 times y to the 3/5 times 5/2. 9 to the 5/2. So we saw some cases where we just raised the number to a rational exponent, and that was the final answer because we couldn't simplify. Can we simplify 9 to the 5/2? Yeah, what do we focus on? The denominator of the exponent is 2. So we want to check to see if the base number 9 is a perfect second power or a perfect square. And it is. 9 is a perfect square. 3 squared is 9. So that means we can simplify this. As an intermediate step, we can write it as 9 to the 1/2 to the 5th, because 5 times 1/2 is 5/2. Let's go ahead and simplify the variable parts. X to the 2/5 times 5/2 is x to the first, and y to the 3/5 times 5/2 is y to the 3/2. And 9 to the 1/2 that's the square root of 9, which is 3. So we get 3 to the 5th times x times y to the 3/2. And 3 to the 5th is 3 times 3 times 3 times 3 times 3. If you remember, 3 to the 4th is 81. So 3 to the 5th is 3 times 81, or 243. So our final answer is 243 times x times y to the 3/2. Okay, let's work on the next two. So in this rational expression, the base a is the same. So we're going to be able to simplify until we get a appearing only once with a positive exponent. So in the numerator, we can add the exponents. A to the 3/5 times a to the negative 1/5 is a to the 3/5 plus negative 1/5 divided by a to the negative 11/5. And in the numerator, we get a to the 2/5 divided, and then we're dividing by a to the negative 11/5. And then we can write this as a to the 2/5 minus negative 11/5. And that is a to the 2/5 plus 11/5, so it simplifies to a to the 13/5. Okay, we're out of time. The last one is similar to the one before it, so I'll leave that one for you to do. Okay, that's all we have time for today.